All right. So you clicked, you showed up. That already puts you ahead of the 90% of the people out there. Welcome to day one of the Maths Challenge. This is where things finally begin to change. Over the next 65 days, you and I are going to do the entire O-level IGCSE math syllabus together. Not randomly, not passively, but in a way that's structured, focused, and actually works. Today, we're starting with day one, numbers. And by the end of today's session, you'll have completed your first concept, your first worksheet, and your first win. See, I'm not here just to teach. I am here to challenge you. And this is not just about watching me do maths. This is about you showing up every day for 99 minutes and getting it done. I'm sure you've tried playlists before. I'm sure you've tried hours of content before. But this time, this is a system. And there's tracking, there's finish line. And this time, this is not passive watching. This is time you and I would actually be doing shit together. Before we jump into this, I want you to pause for 5 seconds and say it out loud. I am in it for 65 days. That mindset shift is where magic begins. This challenge is free, of course, but that doesn't mean it's cheap. It costs effort, consistency, and focus. So now grab your notebook, grab your calculator, let's lock in. Day one starts right now. We have a 7-point agenda today. We are looking to cover 7 topics today. Integers, prime numbers, prime factorization, perfect squares and cubes, factors and multiples, LCM and HCF, and irrational and irrational numbers. So first of all, what are integers? Well, integers are numbers that, you can think about it this way, numbers that come in full. Numbers that come in full, which means we do not allow any decimals and we do not allow any fractions. Okay, so you would say like numbers which are perfectly complete, where you have no parts allowed. What do we mean by that? For example, 1, take 1 for example. 1 is a perfect number, it's perfectly complete, right? But if you take 1.5, that's not an integer because it's a part. You take 3/4, that's a part, right? If you take 5, that's a complete number, so it'll be an integer. If you take -8, that's a full number. Although it's negative, but it's still a number, right? Fully complete number, no decimal. If you take 8.0, that is still a full number. I mean, you can take off 8.0 very conveniently and will still be an integer. Even in this form, it's still an integer. Okay, so the numbers that come in full, it's perfectly, like numbers which are perfectly complete, no parts allowed. Right. So, for example, if you look at a number line, you will see we have a 0, we have a 1, 2, 3, and 4, and so on. Like it goes on and on. And on the other side, we have -1, -2, -3, -4, so on and so forth. The list just goes on, right? So all of them are, I mean, on the negative side, they're called negative integers. All of these are all are negative integers. Okay, and these are all positive integers. All of them are positive integers. Now, if you notice, I'm only counting these numbers: -4, -3, -2, -1, 1, 2, 3, 4. Right? I'm not counting anything in between. For example, 2.5 cannot be an integer. Anything there, for example, 3.1, that also cannot be an integer. Okay? So strictly, the number that you can hop on a number line, that's an integer, right? What about 0? Is it positive or is it negative? And this dude over here is very, very neutral. It's neither positive nor negative. So this guy is neutral. Okay. So all the negative integers, all the positive integers, and a 0, they are integers. Okay, I hope it's simple. Right. How do we represent integer? Well, there are 2 ways of representing integers. One of them is you can write integers, for example, like just like they're written over here. You could write a dot dot dot. You could write, well, -4, -3, -2, -1, 0, 1, 2, 3, 4. You could go on and on, like 5, for example, go on and on. But I do not like this way. Like we have a tail, we have a tail on this side and a tail on the other side, which just goes on and on in both directions. I think a better way of writing it, which is another representation, and that is you can write it this way: 0. Okay. So think about it. We have a positive one and a negative one. How about I write it together like this: positive, negative 1. Right. Take these two, -2, +2. So I might as well write it as positive -2, positive -3, positive -4, so on and so forth. So we have for every positive integer, you have a negative integer. Okay, so here, ladies and gentlemen, this is about integers. It's not, it's a very important concept when we will, by the end of the day, when we'll talk about rational and irrational numbers, we'll understand rational and irrational numbers in terms of integers. Okay, so it's a very important concept to remember. Okay, again, perfectly complete numbers, no parts allowed, no fraction, no decimal, unless the decimal says the same thing. For example, like -3/1. Right? It looks like it's a fraction, but it's actually the same as -3. So it's still an integer. Okay. All right. Next are prime numbers. What are prime numbers? Prime numbers are wolves, lone wolves, right? What would a lone wolf say? A lone wolf will say, it's just me and my shadow, right? So prime numbers are basically the numbers which only have two factors. Okay. Only two factors, right? One of the factors is just 1. The other number is the number itself. Okay. So here's a way to think about it. Think about the number 7. For a while, think about the number 7. Right? Think about the number 7. Can you think of any other pair that would the two numbers that you would multiply and you would get a 7? For example, is just 1 multiplied by 7 is equal to 7, or it will be either 1 multiplied by 7 is equal to 7, or 7 multiplied by 1 is equal to 7. You cannot think of any other pair of integers that you can multiply. Of course, you can multiply 3.5 times 2 and you'll still get a 7, but I'm not talking about non-integers. I'm talking about only the integers, only the positive integers that you could multiply and get a 7. Can you think of any other positive integers that you could multiply that you get a 7? No. Okay, so which means the number 7 only has two factors, like 1, which you can see over here, and the number itself, which is 7. Okay, so these are called prime numbers. Only two factors, not more, not less. I mean, this is why 1 is not a prime number, because 1 only has one factor, that is 1, right? 1 does not have any other positive integer factor. You cannot say 1 has two factors, 1 and the other one number, but if you say the other number itself, the other one will still be 1, so it's the same thing, right? So 1 is not a prime number. Yes, 2 is a prime number because 2 multiplied by 1 is equal to 2, 1 multiplied by 2 is equal to 2, so yes, 2 is a prime number. In fact, 2 is the only even number that is a prime number. Okay, so this is the fact we will use in a while. So for example, 2, 3, 5, 7, I mean, these are the prime numbers you should know on top of your head. 5, 7, 11, 13, 17, 19, and just let's go on and on. We have a lot of prime numbers. But I hope if you think about every number, you cannot 11. It's only 1 multiplied by 11 is equal to 11, or either is it 11 multiplied by 1, which is the same thing, right? So no, not any other positive numbers when they're multiplied can form an 11. Okay, so it's a prime number. Okay, here is exam. So we have exam prep time. In this is a past paper question, by the way. Write the prime numbers between 90 and 100. Okay, so if I were to list down all the numbers between 90 and 100, I would have pointed out, like wrote it down 90, 91, 92, 93, 94, 96, and 98, and 100. Right? Why did I not write the even numbers? Because apart from 2, 2 is the only even prime number. Apart from that, there is no other even number which is a prime number. So if I'm looking for prime numbers between 90 and 100, the first thing I should do is take out all the even numbers, right? Because all the even numbers are divisible by 2. So it is the only prime number. Okay, so the tip is, whenever you're looking for prime numbers, always, apart from 2, always look for even numbers, not the odd. Always look for odd numbers, not the even numbers. Sorry about that. Okay, so let's see which of them is an even number. 91. Is it an even number or an odd number? Is it a prime number or not? It's definitely not a prime number. It's 93 and 93 is easily divisible by 3. I mean, 93, I think if you divide it by 3, you would get 31. 31 times 3 is 91, so it's definitely not a prime number, right? 95, of course, 5 is divisible by 5. 97, okay, 99 is divisible by 3. 99, you can easily divide it by 3. 3 33s are 99, so definitely it is another prime number. 97 is the only lone wolf here, right? So this is my answer. This is the only prime number between 90 and 100. Okay, a little bit makes sense. Next, prime factorization. What's prime? We just talked about prime numbers, right? So prime factorization, you can think of prime factorization as chopping. Right? How chopping? You take any prime number, you take any big number, and you break it down into prime numbers. Right? It's like chopping a big number into prime numbers. Yeah. Okay, so take a big number and chop it into prime numbers. Chopping, you take a big piece of meat, for example, over here. Let's say this is a piece for a steak, and then you chop it into pieces. That's how you take in the same way, you take a very big number, not necessarily very big, but just a big number, and you big number into prime factors. Okay, prime numbers or prime factors. Okay, for example, think about 6. If I can write 6 as 2 multiplied by 3. I just broke down 6 into set of 2 prime numbers. Make sure they're prime. Okay. Let's take another number, for example, 100. You can write 100 as, let's take 50, for example. 50. You can write 100 as 10 multiplied by 2. Will it be prime factorization? Are the 10 and 2 prime factors? The answer is no. 2 is a prime number, yes, but 10 is not. Okay, 10 can be further broken down into 5 and 2. Right? So I can write 50 as 5 multiplied by 2 multiplied by 2. 5 actually. 2, okay, no. 2 multiplied by 5 multiplied by 5. So that's how I mean, 2 times 5 would be 10, 10 times 5 would be 50. Okay, so if you notice, if all of the pieces are prime numbers, then that process would be called prime factorization. Now, it was easy for us to do prime factorization of 6 and 50, which is, it seems like it's quite easy, but not all prime. What if you have a really big number? Let's say I ask you to prime factorize, 1096. Would you be able to do it by using mental maths? No, I'm not expecting you to do this, by the way. We have a method of doing prime factorization, and that's a very simple method. You take a number, right, and you make a table like this, and then you think of a prime number that divides 72. So it's 72 is an even number. It should be very simple. I could just write 72 as 2. If I write 2 here, I would get a 2 multiplied by what is 72? I think 2 multiplied by 36 is 72. Right? You can do it again with 2 because it's still again an even number, 2. So I'll get 18. It's still an even number. I can still do it by 2. Look for the smallest prime number, right? That's the key. Do not like start off by multiplying with 13. Look, 13 is also a prime number, but start with the smallest prime number. That's the key here. Essential tip actually, start with the smallest prime number. Okay. All right. I can do it to 18 as well. I will get a 9. Now, 9 is not an even number. I cannot divide it by 2. So I'll divide it by 3. 3 3s are 9 and 1. Okay. So I got all the prime factors over here. It's like a machine. You give it a big number and you keep on processing it and you keep on getting the pieces or the choppings of the big number, all the prime number choppings of a big number on this side of the table. Okay. So I can write 72 as Take 72. I can write 72 as, 2 multiple, it is 2 3 times. So 2 times 2 times 2 times there's 3 and there's 3. So another way of writing this would be we have 2 3 times, right? 2, 2, and 2. I can write it as 2 to the power of 3 multiplied by 3 to the power 2. Again, this is for this one, and the other one is for. Okay, I hope it makes sense. I hope it's not so difficult. All right. So that is about prime factorization. We'll come to the exam style questions of prime factorization in a while. Next we have is perfect squares and perfect cubes. What is a perfect square, right? What's a perfect square? When you love yourself so much that you marry yourself. Sounds weird, right? That you marry yourself. You'll get a prime perfect square. For example, if let's say you're 2, right? And then you marry yourself, that is, you multiply yourself with another same number, you'll get a 4. So the same positive numbers, when they're multiplied, the same positive integers, when they're multiplied, you get a perfect square. For example, 3 multiplied by 3 is 9. Right? 8 multiplied by 8 is 64. Make sure the two numbers are the same. The two numbers that you're picking over here, the two numbers should be the same. Okay. Right. Now, what's a perfect cube? Again, the similar. When you love yourself, now over here it's so much, but over here it's so much that you marry yourself thrice. And I know, sounds cheesy. Marry yourself so much that you marry yourself thrice. Like, in other words, in simple words, the same number multiplied 3 times. Okay, for example, over here we multiplied 2 twice. Over here we'll take the same number, for example, and we'll multiply it thrice. 2 multiplied by 2 multiplied by 2, which will be 8. Double 3 multiplied by 3 multiplied by 3, it will be 27. Okay. Now, sadly, there's some memorization that you need to do. Cambridge requires you to memorize. Do they want us to memorize all the perfect squares in the word? No. They memorize us. They require us to memorize the perfect squares from the numbers 1 to 15. Although I would recommend to learn the perfect squares of the numbers 1 to 20. I would really recommend that. Okay, but the requirement, I think the bare minimum requirement is to learn the perfect squares of 1 to 15 and perfect cubes from 1 to 10. So I'll write the perfect squares. Okay, 1 multiplied by 1. Okay, 1 multiplied by 1, can I write it as 1 squared? Actually, write it as 1 squared. Can I write it as 1 multiplied by 1? There will be just 1. These are the blue ones are all the essential ones. These are the ones that you must know. You should be able to know and actively recall while doing a question. All of these perfect squares. So when you multiply 1 with 1, you get a 1. Multiply 2 with 2, you'll get a 4. If you multiply 3 twice, you'll get a 9. 4 times 4 would be 16. These are all the perfect squares and perfect cubes all the way up to 20. Okay, learning up to 15 is mandatory. All the way up to 15 is mandatory, but this box is completely optional, although very, very recommended that you learn that. Okay, it's going to help you a lot. This box is recommended. Okay, yeah, maths is about memorizing, no matter what your math teacher tells you. That is not about memorizing. Okay, perfect cubes. Now the same thing, but the only difference is you take the same number, you multiply it twice. Okay. Now we have some ease over here. You need to know all the perfect cubes all the way up to 10. Okay, so it should be simple. 1 multiplied by 1 cubed would be equal to 1 multiplied by 1 multiplied by 1. 2 cubed would be equal to 2 multiplied by 2. 2. Right. Now let's write down the perfect cube. If you multiply one thrice, it's a simple one. You get a 1, you'll get an 8, you'll get a 27. If you multiply 4 thrice, you're gonna get a 64. These are the numbers which are mandatory that you know and you should be able to recall. Okay, more importantly, you need to recall it backwards. Like when you see 27, you should be able to tell that it is 27 actually is 27 actually is a cube of 3. Okay? You need to learn it backwards, not forwards. You can easily tell 4 cube is 64, right? When you see 24, when you see 64, do not lose your mind. Learn it backwards as well. 64 is actually 4 cubed. That's the stuff that you need to memorize. All of it. I will put it somewhere right here. That's all the stuff that you need to memorize. Where should I put it? I think it's fine here. Okay, next. So we have some past paper questions. Let's see how we can tackle them. So express 60 as product of its prime factors. I hope you understand now. We did prime factorization. It's like chopping, again, chopping. Take a number and chop it into prime factors. So let's do that. 60, 60, 2, 30. And if we do it again, 2 15s are 30. Take it again. And now I cannot further divide it by 2, so I'll take the next prime number. Okay, do not go for 5 right away. Take the next prime number after 2. The next prime number is 3. So 3 times 5 is 15. Now you have no choice but to take 5. So I'll take 5 and 1. Okay, so I have all the prime factors over here on the side of the table. Pretty simple, right? So 60 is equal to 2 times 2 times 2 times 3 times 5. You multiply 2 thrice, you'll get a 2 cubed times 3 times 5. So that is my answer, times 3 times 5. Okay? Actually, no, it's not 2 twice, not thrice. My bad. 3 multiplied by 5. Right? So 2 squared times 3 times 5. So with 2 squared. Okay? Right, find the smallest possible number m such that 60m is a square number. Now, how do we know which number is a perfect square? Right, if you notice over here, when it comes to square, you need pairs. 1 squared. It could also be like, for taking some other perfect square, it will be 1 squared times 2 squared. Okay? Any other perfect, that will give you 4. 3 squared times 4 squared, you'll get some other number which will be a perfect square. Right? So what do we need for a number to be a perfect square or a square number? The prime factors, and this is very important because this is a very repetitive question in the exam. All the prime factors must be in pairs. Okay, so for example, if I write 60 as 2 squared times 3 times 5. If you notice, 2 is a perfect pair, right? But 3, there's a partner of 3 missing, and then you have a partner of 5 missing. That is itself, right? So I'll write, if I were to write it as 60, if you notice, this is 60m. If I write it as 60m, now I've put an additional m over here. What would I do on the other side? To make up for m, I'm going to write everything that's missing. Okay, so 3 multiplied by 5. What's missing? There's a partner of 3 that's missing. Multiply by 3. And there's a partner of 5 that's missing. So this will be my deficiency. If I were to put that in, if I were to put 3, another 3 and another 5, then 6, then this whole thing would be a perfect square, right? Which means I need to multiply 6 by 60 by this number, 3 times 5. So which means that is my m. M is equal to 3 times 5, which is 15. So m is equal to 15. Okay. Now, try this, and I think it's really, really important that you take a pause and do this by yourself. Okay. It's really simple. And if you're not doing this by yourself, you're just watching, you might as well watch it in the YouTube playlist because this is not supposed to be passive watching. Okay. So I would really encourage you to take a pause and try this by yourself. Give it a shot. All right, next. Write down 54 as a product of his prime numbers. So we'll do the same thing. I think it's nothing different now. 54, it's an even number. I can divide it by 2, 2, 4, and I think I'm gonna get 2. I'm gonna get 27. Okay, and I cannot divide it by 2 anymore, so I'll divide it by 3. 3 times 9 is 27, right? I'll divide it by 3 again. 3 times 3 is 9, and 3 times 3 is 1. So I can write 54 as 2 multiplied by 3 multiplied by 3 multiplied by 3. In short, I can write it as 2 multiplied by, we have 3 thrice. So I can write it as 3 and put a cube on top of it. Okay, pretty simple. Now, the same logic, find the smallest smallest possible integer m such that 54m is a cube number. Okay, so the same logic applies but kind of differently. Over here we were looking for pairs. Must be in pairs because we're looking for a perfect square. Right? The same logic will apply, but now in the perfect cube all of the prime factors must be not in pairs but in triplets. Now we have to have 3 of each prime factor. Okay, so let's see how that goes. All of the prime factors must be not in pairs, but in triplets. Okay, so I think it should be simple now. 54m is equal to, okay, I'll write 54 first. 54 is equal to 2 multiplied by 3 cubed, right? So 3 is a perfect cube. I don't need to worry about it. I need, because I love myself so much that I need 3 of me, I need a triplet, but there's only one of them. Okay, so I need, if I were to write 54m, right, then what I can do is 2 multiplied by 3 cubed. I can put in place of that, I'm going to go 2 squared over here because 2 squared and a 2 will make a triplet. So which means this is the missing piece of the puzzle. We figured out the missing piece of the puzzle, and m is equal to 2 squared, which we know is 4. So m is equal to 4. I hope there's no confusion about this. Okay, it's the same thing as the one we did over here, but this one is for the cube numbers. Okay, let's move on. I would encourage you to do this. Same thing, it's become all the way more easier now because the prime factorization is given. So you don't need to do prime factorization all over again. You're given the prime, all the prime factors. All you need to do is complete the triplets. Okay, so I think I'll give you here, you need to multiply it by 3, and there's 1 5, so you need 2 more 5s. Okay. Nope, not telling you. You're supposed to do this on your own. Next, factors and multiples. What do we mean by factors and multiples? Think about seed and fruits. Think about seed and fruits. A plant is made up of a seed, right? But it gives fruits. Okay, seeds are limited, that gives a plant, and fruits are unlimited. This is exactly behind the concept of factors and multiples. Okay, so seeds, they make up a plant, right? In the same way, factors make up a number, and fruits is what is given out by a plant. In the same way, multiples are everything that is given by a number. What do we mean by that? Let's take an example. Okay, you can think of factors as factors go in. Factors go in, which means it's like going in, they make up a number, and multiples go out. Multiples come out, actually. Just like fruits coming out of, fruits coming out of a tree. Okay. Let's take 6. Let's take a number 6, for example. Take a number 6. Now, if I ask you to write it on the factors of 6, you will write 6 as 3 multiplied by 2, right? 2 multiplied by 3 is the same thing. both prime numbers. So I will say the factors of 6 are 3 and 2. So factors of 6, 3, and 2, right? It's pretty simple. Now, what about the multiples? Multiples is something that come out of a number. For example, it's like fruits again. Think about the multiples of 6. So if you take 6 and you 6 multiply by 1, you'll get a 6. But if you multiply 6 by 2, you'll get a 12. If you multiply 6 by 3, you're gonna get 18 and so on. Will it ever stop? No. Okay, it is never ending. You can multiply by the biggest of the numbers and you will still get multiples. Okay, so multiples are normally bigger than number. They're equal to the number as well, but normally they're bigger than a number. You can also write 6 as 6 multiplied by 1. 6 multiplied by 1. So factors of 6 would be 1, 2, 3, and 6. Okay, they do not need to be prime factors. They could be any factors. Okay, I'll put that here. We're not talking about not necessarily. I know my spelling is messed up. Not necessarily prime factors, but could be any factors, right? Okay, so can I say that factors are limited? Okay, factors are limited stock. Okay. Factors are limited, while this is an unlimited stock. Okay, which means factors are unlimited. Multiples, I'm so sorry. Multiples are, you can have as many multiples of a number as you want, but you cannot have infinite amount of factors of a number, right? Multiples are unlimited. Okay, I hope there's no confusion about factors and multiples, right? Whenever you get confused about the factors and multiples, think about the seed and the fruit. Seed is a factor and fruit are multiples. Limited seeds, but you can have unlimited fruits. Of course, not exactly unlimited, but again, a lot of fruits. Okay, I hope the analogy makes sense. I hope everything makes sense. So okay, so factors and let's come to the proper definition. I mean, we've been bantering up until now. Factor is a number that divides a number completely. That divides a number completely without leaving a remainder. Okay, so if I'm claiming that, okay, let's say factor 9 is a factor of 18, right? Then I will, if I were to divide them, I should get without leaving. Yeah, the remainder should be 0. 9 2s are 18. I should get a 0 remainder. But 7 is not a factor of 18. If I were to divide 7, I can divide, yes, but I'll be left with a remainder. 7 2s are 14, and I'm left with a remainder. Okay, so the numbers that divide a number completely without leaving a remainder. If you think about it in terms of this division, over here, from here, I can conclude that 9 is a factor of 18. But 7 is not a factor of 18. Okay? So far, so good? Right. So if you write multiple on top, if you write factor at the bottom, what do you think should happen? Let's take an example. For example, if you write 18 on top, and if you write factor at the bottom, let's say 9 is a factor. If I were to further simplify to break it down into prime factors, it will be 3 multiplied by 3 multiplied by 2. This would be 3 multiplied by 3. If I were to do the cancellation, 3 will cancel out, this 2 will cancel out, I will just left with 2. Okay. But if you have a factor, if I'm claiming there is a multiple on top and factor at the bottom, the factor at the bottom should cancel out completely. For example, if I were to write, since 9 was a factor, so the factor disappeared, right? But if I were to write 18 divided by 7, I would get 3 multiplied by 3 multiplied by 2 divided by 7. It wouldn't cancel out. So if the denominator does not cancel out, this is one of the ways to know whether a given number is a factor of the numerator or not. Okay? If it cancels out, for example, 7 does not cancel out, so it's not a factor. 7 does not cancel out, so it's not a factor. So whenever factors and multiple are written like this, new denominator should all cancel out. Denominator must cancel out. Okay, I just gave you an example. I guess I should write the example over here. This is a factor. The other one was a counter example. This is not a factor. I know I'm making a lot of mess here, but bear with me. That's what I do. Okay. How do we know 5 is a factor of 45? Well, let's apply the same thing. For example, if I write 45 on top, multiple is on top, and if I want to know 5 is a factor, I'll write 5 on bottom. Let's see, 45, if I were to break down 45, that's real quick. 45, 3, I think 3 15s are 45, 3 5s are 15, and 5. So I can write 45 as 3 multiplied by 3 multiplied by 5 divided by 5. Can I cancel out 5? Yes, I'll be left with the denominator cancels out. I do not need to know anything further. So denominator all cancels out. Yes, it is a factor. Okay, because it cancels out in the denominator. If it's written in the denominator, it cancels out. Let's see if 14 is a factor of 84. I'll put 84 on top. 2 4s are 8, 2 2s are 4, 2 2s are 4, 2 1s are 2. I think I should write divided by 3, 3 7s are 21, and 7 times 1. So 2 square, I can write 84 as 84 divided by 14, which is 2 multiplied by 2 multiplied by 3 multiplied by 7 divided by 14. You can do the same for 14 as well. 14, 2 7s are 14, 7 1s are 14. So I'll write it as 2 multiplied by 7. Now, does the denominator cancel out? Let's see. I think I can cancel out 2 with a 2 and 7 with a 7. So yes, if the denominator cancels out, it is a factor. 14, is 14 a factor of 4? Yes. Is 5 a factor of 5? 45? Yes. Okay, let's check it for 20. So I can write 20 as 20. If I put 20, I can write 20 as 2 10s are 20, 2 5s are 10, and 5 1s are 1. Okay, let me write it as a decimal first, as a fraction first. So 135 divided by 20, which is 20 is 2 multiplied by 2 multiplied by 5. Let's do the prime factorization of 135. 135, 2 6 are 12, I think. 63, and I'll divide it by 3. 3 2s are 6, 3 1s are 3. And 3 7s are 21, and then 7 1s are 7. So 2, 3, 3, and 7. Looks like there's a problem. The problem is 2 cancels out, 3 does not cancel out, and 5 does not cancel out. Okay, so we have something left in the denominator, which tells me that, that 20 is not a factor. If it were a factor, then the denominator would have canceled out. Okay, I hope it makes sense. This is a very important and a handy check to know whether something is a factor of a given number or not. Okay, now let's take on some exam prep questions. These are the past paper questions. The number 225 and 540 written as the product of their prime factors. 225 and 540. So prime factorization, the chopping of the numbers, if you remember, is already done for us. Write 2250 as the product of its prime factors. Right. Now, if somebody is really dumb, what the person would do is write 225 and then 2250 and would do all the prime factorization all over again. But if you notice smartly, 225, right? 225. How would is there a way I can turn 225 into 2250? Yes. I could just multiply it by 10, which means, okay, if I have written 225 is equal to 3 squared multiplied by 5 squared, what I could do is I could take the same thing, 225, and I could multiply it by 10, right? You could say 2250 is 3 squared, the same thing, but multiplied by 10. Now we'll have to do one more thing, and that is break down. 10 is not a prime number. So I have to break down 10 into prime factors, and that's it. 3 squared multiplied by 5 multiplied by, if I were to break down 10, I'm going to get 2 multiplied by 5. Right? So if I were to rearrange it, I'll write 2 in the beginning, multiply by 3 squared, multiply by, there are 2 5s, so 5 squared. And that is how I will write 2250 as a product of its prime factors. Okay. Right, next, the smallest positive integer n, value of n for which 225n is a multiple of 540. What does it mean? It means if this is the multiple, then this would be the factor. Right? Now, if you notice from above, which we just saw a while ago, this is part 1. We just saw a while ago that if I write multiple on top and factor at the bottom, all the factors should cancel out. Okay, denominator must cancel out if something is a factor. Now, it's already given that 540 is the factor, which means if I write 540 at the bottom and 225n on top, well, will they cancel out? Now, of course, I'll have to write it as prime factors, and luckily, all the prime factors are given to me. Okay, so I could write them like this. So 225 would be 3 squared multiplied by 5 squared divided by 540 is 2 squared multiplied by 3 squared multiplied by 5. All right. So does the denominator cancel out? Let's see. 3, actually copy it again for the cancellation. Now 3 squared cancels out perfectly. It's actually 2 squared, 3 cubed. Okay. Now 3 squared is gonna cancel out with 3 squared, and I'll be left with I'll be left with just 3. Okay. And 5 will cancel out. I'll be just left with 5 at top. Actually 225n, so I'll write n over here as well. Okay. Now what does not cancel out? I'm left with 1 3 and a 2 squared. 2 squared doesn't cancel out and 3 doesn't cancel out. Okay, which means only if I had 2 squared and 3 on top, they would have canceled out, and this thing, the bottom would have been the factor. Okay. So which means I need to multiply 225 by n, which means I need to multiply 225 by 2 squared multiplied by 3 so that the bottom can be the factor. I hope you understand. Okay, so which means n should be equal to whatever is the highlighted one, 2 squared multiplied by 3, so that if I had 2 squared and 3 on top, they would have canceled out and the bottom cancels out completely, which makes the top a factor. Okay, which means the top should have been 2 squared, at least it should have been 2 squared times 3. Okay, so n is equal to 2 squared times 3 would be 4 times 3, which is 12. So n is equal to 12. Okay. This is again one of the very common exam questions, but if you get the logic behind that, if you know that, okay, all the denominator needs to be canceled out, then you'll be able to crack this question very easily. Okay, I'll let you do this one. Take a moment again. Pause the video, take a moment to do this. Yeah. Again, I'm telling you, if you're not doing that, you're not getting anything out of the video. All right, now the next very important concept, and that is LCM and HCF. What do they even mean? LCM means least common multiple. are, in other words, also called lowest common multiple. Lowest common multiple. Okay. And HCF means highest common factor. Okay. Now, what even is this? What even is the lowest common multiple and highest common factor? A lot of words, a lot of words. They sound like they're a lot of words. Okay. So to help understand what do we mean by LCM and HCF, let's take two numbers, 6 and 8. So can you tell me what will be the factors of 6 and 8? If I were to write the factors of 6, I think 1 is always a factor of anything. 2, 3, and 6. They are the factors of 6 because all of these numbers somehow they make up 6. Remember, factor is the seed, and multiple is the fruit. Fruit is whatever comes out of a plant. And take 8, for example. What will be the factors of 8? I think 1, 2, 4, and 8 itself. The number itself is a factor of itself as well. Okay, because 8 times 1 is equal to 8, right? Okay, now what about the multiples of 8? Let's see. 6 1s are 6, 6 2s are 12, 6 3s are 18, 6 24, 6 5s are 30, 6 6 are 36, so on and so forth. Look at the number 8. 8 1s are 8, 8 2s are 16, 8 3s are 24, 8 4s are 32, and so on. Okay. So multiples are ever going. They don't stop. There's just an infinite list of numbers. Well, factors are finite. Just end there. Now, I'm comparing the factors and multiples of two numbers, right? Now, if you look here, what is the highest? Now, listen to this closely. What is the highest factor that is common between the two? What do you think? And the biggest number, of course, there's 1 as well, right? But 1 is not the biggest number that's common. I think it's 2. Is the biggest number that is common. So the biggest number that is common is 2. So 2 will be my HCF, the highest common factor. I hope the word now makes sense, right? I'll pick up something which is highest, which is the biggest, the largest, and something that is highest and also common. Highest and common and a factor. Okay, so we can clearly tell from here that it's actually 2. Okay, so HCF, or the highest common factor, is 2. Okay, now what about multiples? Now for multiples, I cannot, I'm looking for the opposite. Over here, I was looking for the highest number. The next, I'm looking for the lowest number, the smallest number. I'm sorry. Over here, I was looking for the highest one. Over here, I'm looking for the smallest number. That is the highest number, the smallest number. I'm sorry, I got distracted for a while. The smallest number that is a common multiple of both. So I think I can tell 24 is the smallest number, which is common across both. Over here, it is 2. Right? So I will say the least common multiple. Okay. A multiple, first of all, it should be a multiple, then it should be common, and then it should be the smallest. Okay, if you keep on going, you might find something other, for example, 720. Let's say that's also common, but that's not the least common multiple. That's a multiple that's common, but that's not the least, right? So pick up something which is the least common multiple of the two. Okay, right. So I think the least common multiple would be 24 over here. I hope it makes sense. Okay. Now there are ways, of course, if the numbers are really big, I cannot write all of the common factors like this from the top of my head, and I cannot write all the common multiples by myself. Over here, the numbers were small numbers, so I could have done that, but there should be some way, there should be some technique, some method to evaluate that, right? So there are actually two ways of calculating LCM and HCF. Okay, of course, the both ways include prime factorization. One of them is called the single table technique, and the other one is called the separate tables technique for calculating both the LCM and HCF. Now, why the two techniques? Because the exam questions vary. Okay. Sometimes you need to apply, sometimes in some questions, single table technique is more useful. Sometimes the separate tables technique is more useful. Okay, so should be able to pick the technique. You don't have a choice. You need to learn both because some question requires you to do separate tables technique and some question requires you to do the single table technique. Now, what even is a single table technique? If you remember prime factorization, again, prime factorization was chopping numbers into prime factors, if you remember. Prime factorization I'm talking about. Right. Let's take two numbers, 12 and 16. Okay. Now, this is a single table technique. In this technique, we will write them in a single table. So 12 and this is not minus, this is a dash between 12 and 16. All right. Now 12 and 16. Okay. We'll draw single tables for both of them. Now the procedure is almost same, but there is a very slight difference between the two. Okay. If you pick that difference, you'll be able to easily do both of them because the method is kind of same. We should also be able to differentiate between the two. Right. So how would I calculate HCF? I will do the same thing. I'll pick up a number that divides both. Okay. This is a very common trick. Pick a number. Pick a prime factor that divides both. Okay. The difference is over here, you have to pick a factor, pick a prime factor, pick a prime factor that divides any of the two numbers. Okay, that is the very common difference between the LCM and HCF. Okay, let's see how it plays out. Let's see what do we mean by a prime factor that divides both and a prime factor that divides any. Let's find out. Okay, so pick up a number that divides both. Okay, let's keep that in mind. Let's try to follow that. 2, 6 are 12, 2, 8 are 16. If I pick up, I think I can pick up 2 again because it divides both, right? 2 3s are 6, 2 4s are 8. Now, can I pick a number that divides both 3 and 4? I cannot think of any number that divides 3 and 4. So I'll stop here. Okay, at this point, I can't think of any number that divides both. Okay. So can't think of any number that divides both. I would tell myself to stop here. Okay. And whatever I got on the left-hand side, this is my HCF. Highest common factor is 2 times 2, which is 4. I think pretty convenient, right? Okay, now the same thing will follow in LCM, but with a slight difference, and that is pick a number that divides any of the two. So I think the easiest would be 2. If I do 2 6 are 12, 2 8 is 16, then I'll pick 2 again, 3 and 4. Now, if I were doing HCF, I would be stuck over here because I cannot think of any number that divides both of the numbers, right? But I don't need to. I'm doing LCM. I can pick a number that divides any of the two numbers. Okay, so I think I'll pick the smallest one. If my 2 doesn't divide 3, that's fine. I'll carry on 3 as it is, and I'll keep on picking the smallest prime number that divides any number. So 3 will carry on, and it'll be 1. Right now, I think the next prime number that divides 3 is 3 itself. So 1 and 1. Okay, and I'm done. Of course, I cannot do it anymore. So over here, here's a tip: know when to stop, right? Over here, when you got 1 at the end, at the and stop. Okay, and that's done. We're done. We found out some. Everything we got on the factor side is the LCM. Okay, pretty convenient. LCM is equal to 2 multiplied by 2 multiplied by 2 multiplied by 2 multiplied by 3, which is 2 to the power 4 times 3, which is, I think, 16 threes are what? I think 48, if I'm not wrong. Yep, 48. 48 is my LCM. Okay, so this is the simple table technique. I think pretty convenient, right? There's not a lot that you need to do, and you get your LCM right away. Okay, so this that we did a while ago, you make factors and multiples. I was doing it by thinking. Okay, so this is more of a thoughtful process than a procedural process. This is more of a procedural process. There is a set procedure that you have to follow, and you will land yourself at the answer. Okay, if you were to ask me, I prefer procedural things more than conceptual things. If you were to ask me to think and write, I mean, that is for the most of the students. I might have a hard time. But if you were to ask me to follow a procedure, I would happily follow a procedure that would lead me to the answer. Okay, so always when you're looking for maths explanations, always go for the procedural ones. Okay, once you do the procedure enough times, you will get the concept behind it as well. Okay, but if you're looking for the concept and just doing it through concept, you might face a hard time. Right, now let's take the same numbers 12 and 16 and let's apply the separate tables technique. In separate tables technique, as the name suggests, you need to make separate tables. Over here, I just made a single table and I dealt with them in a single table. But over here, I'll make separate tables for them. Okay, so I'm doing HCF here, and I'm doing LCM here. Okay. And of 12 and 16, of course, I'm picking up the same numbers and see if I'm getting the same results by different techniques. So I'll make separate tables, of course. So 12 and 16. I'll copy them over to, I'll actually do it all the prime factorization, and then I'll copy to the CF. Okay, so 12 and 16, if I were to do the prime factorization, I think this is 2 6 are 12, 2 3s are 6, 3 1s are 3. I think for 16, 2 8s are 16, 2 4s are 8, 2 2s are 1, and 2 are 2. Okay, I hope it makes sense. Right now, this is something we've been doing so far. What's the difference? Let me also copy the same. Actually, let's do HCF first. I'll write the factors. The factors for 12 would be 2 multiplied by 2 multiplied by 3. The factors for 16 would be 2 multiplied by 2 multiplied by 2 multiplied by 2. Okay. Now, how would I calculate the HCF? I think I need some space here. Let me make some space. Okay. Now, how do we calculate HCF from here? HCF, this is the formula for separate tables technique. Please remember this formula. HCF is equal to just the common factors. That's it. You take out the common factors and then you multiply them. Okay. So what's the common factor here? I think 2 and 2. So HCF will be equal to 2 multiplied by 2, which is 4. Okay. Now let's calculate the LCM. Again, I have to make separate tables, so why not I just copy these tables over to the other side. Right. Now I'm also going to write the same factors. Okay, because factorization process is the same. The only difference is how we manipulate or how we interpret the factors. And how, in other words, how do we get out our LCM from the factors? Okay. One sec. Okay. So of course, LCM is equal to common factors multiplied by uncommon factors. Okay. That's the goal here. Okay. Well, how do we follow that? Let's see. What are the common factors? We already know what the common factors are. 2 and 2. So write down the common factors. And the common factors will be, actually, LCM would be equal to, common factor is just 2 multiplied by 2. I'll put that, 2 multiplied by 2. What are the common factors? If you notice, there is a 3, there is a 2, and there is a 2. So I'll 3 multiplied by 2 multiplied by 2. If I were to multiply everything, I will get my LCM, which if I do everything, I'm going to get 40. 48 actually. So that is my LCM. I hope you understand the separate tables technique and the single table technique. Okay, again, I'm insisting on this point that you need to learn both the techniques to be able to understand LCM and HCF completely, because both the techniques are used in different types of questions. Okay, again, you don't get a choice, you need to learn both. Written as a product of its prime factors, which means there's a number 360 and you're already given its prime factors. Okay, what are you supposed to do over here? And there's another number 108. I have to write it as the product of its prime factors. I don't think it's a big deal. I could do that very easily. 108, if you divide it, you do prime factorization, 2, and it will be 54. And then again, if you do 2, 2 2s are 4, 1 will be carried out, I think 27. I think 3, because 27 is not an even number, so it will be divisible by 3. So 3 9s are 27, 3, 3, and 3 and 1, okay, which means that I just 108 is equal to 2 multiplied by 2 multiplied by 3 multiplied by 3 multiplied by 3, because 3 is 3 times. Okay. Now, find the lowest common multiple of 108 and 360. Now, can you guess the method over here? If I have the lowest common multiple is the same thing as least common multiple, which is I'm trying to find out the LCM. If I have to do, even if I pick the method of a single table, I would have to do the prime factorization all over again in a single table from scratch, I think, to do whatever. I'll have to do it all over again. But if I pick it the separate tables method, the convenience is I already did the prime factorization of 108. I don't need to do the prime factorization of 306. The factors are already given. All I have to do is to write out the factors, just like we did a while ago. Write down the factors and take out the common factors and multiply them with the uncommon factors, and that's it. You'll get the LCM. So I think the better strategy over here is to pick the separate tables strategy. Okay, we already have the factors of everything, so we don't even need to do the separate tables again. I could just write the factors. The second tip over here is, I think I forgot to mention here, that in the separate tables method, write down the factors, open up all the factors. Okay, do not write factors in the exponent form, but rather open up the exponents. Open up the factors. Okay, which means instead of writing 2 squared, write it as 2 multiplied by 2. Okay, so you can it'll be easy for you to take out the common factors. Okay, I'll do the same over here. I need to find out the LCM of 108 and 360. So I'll write down 360 is equal to, I'll open up the factors, 2 multiplied by 2 multiplied by 2 multiplied by 3 multiplied by 3 multiplied by 5. This is what I did for open up these factors. And now I'll write the factors of 108, which are 2 multiplied by 2 multiplied by 3 multiplied by 3 multiplied by 3. Okay. Now I'll take out the common factors, of course. If you remember, LCM is equal to common factors multiplied by uncommon factors. Right? uncommon factors, right? So common factors will be, if I were to do the common factors, one common factor, another common factor, I think another common factor, I think another common factor. So the common factors are 2 multiplied by 2 multiplied by 3 multiplied by 3 multiplied by what am I left with the uncommon factors? I think the uncommon factors are 2, 5, and 3. So I'll put them here. 2 multiplied by 5 multiplied by 3. Okay. So I think once you calculate that, you will get your answer. You can use a calculator for this, by the way. Okay. So once you use a calculator, I think you will get you're gonna get 1080, and that is your answer, 1080. All right, so I hope it makes sense. Right? In the similar way, I want you to do this. Write 154 as a part of its prime factors, and then find the lowest common multiple of 154 and 49. So you'll have to pick up the strategy, whether you could use a single table or, I mean, you have to figure it out for yourself, whether you have to use a single table or separate tables, totally up to you over here. Okay, right, next. I mean, it's simple because you're already doing the prime factorization of 154. So, and 49 is just 7 multiplied by 7. So you don't need to use a single table. You could write down the factors and do the common factors multiplied by uncommon factors. That's fine. Okay, you need to do this by yourself as well. Now, if you notice, you're written as you're given the common prime factors, which is great. You need to find out the largest integer, which is the factor of both 294 and 784. Take a moment and think about this. Are you being asked the least common multiple or highest common factor? Largest integer means highest. Okay. Both means anything that is common for both. So highest common and factor. So basically, you need to find out the highest common factor of 294 and 784. I don't think it should be a big deal. You will be able to do it easily. Right. Next, I think this is pretty simple. I would say I wouldn't do it for you. I would say try to do it by yourself now. 140 as a product of its prime factors. All the prime factors of 168 is given. Highest common factor HCF. I think we haven't done an HCF question like a past paper question. Let's do an HCF question. Okay. So 168, I'm given the factors of prime factors of 168. I could just write prime factors of 140. 2, and this would be 70, 235, 5, 7, 7, and 1. So 140 is equal to 2 multiplied by 2 multiplied by 5 multiplied by 7, right? And now, highest common factor, I'll write the factors in the expanded form, 2 multiplied by 2 multiplied by 2 multiplied by 3 multiplied by 7. Where am I getting this from? I'm getting it from there. Okay, I just opened them up. Now, 140 is equal to 2 multiplied by 2 multiplied by 5 multiplied by 7. I think you can take out the... Now, in HCF, you only take the common factor. Okay, you do not multiply the uncommon factors, you take out only the common factors. So 2 is a common factor, and again, 2 is a common factor, again, 7 is a common factor. So HCF will be equal to common factors, which is 2 multiplied by 2 multiplied by 7, which is, I think, 4 multiplied by 7, which is 7 4 is what? 32, I think. 28, sorry. It's not 28. Okay, so 28 is my answer. Find the smallest positive integer n such that 168n is a square number. I think we did this, we did a question like this before as well. You write down the factors of 168, 2 cubed, multiplied by 3, multiplied by 7. Now 168n is a square number, which means to make it a square, I need to make up pairs. So 3 cubed multiplied by, if I were to make pairs, right, I would split it 2 squared multiplied by 2 multiplied by 3 multiplied by 7. Over here, I splitted 2 cubed into 2 squared multiplied by 2. Okay, so that I can make perfect pairs. And over here we have 168, right? Now, what's missing? There is an incomplete pair. I need a 2, I need a 3, I need a 7. So what I'll do is I'll put an n here instead of n. I can multiply in place of n on the right hand side. I could multiply a 2, a 3, and a 7. So my n is basically whatever I have added by myself, just to complete the pairs. Okay, so 2 will now be coupled with this 2, this 3 will now be coupled with this 3, and this 7 will now be coupled with this 7. Right, so you will get n is equal to 2 multiplied by 3 multiplied by 7, which is 2 3s are 6, 7 6 are 42, I think. Yeah, 42. Okay. So in other words, if you do 168 multiplied by, you can do this by on a calculator as well. If you do 168 multiplied by 42, and if you square root that, you're going to get an integer. Okay, you can try this on by yourself. Right. Next, word problems on HCF and LCM. Let's see. So this so far we've been doing LCM and HCF theoretically, just numbers. It's told you a bunch of tips and tricks, and we're following that to solve the questions. But in the real life context, how does it work? Let's find out by doing a question. Green line buses run every 10 minutes. Red line buses run every 20 minutes. Purple line buses run every 35 minutes. One bus from each line leaves the city center at 9. After how many minutes will buses from all 3 lines leave the next city center at the same time? Okay, so here is a city center line, and if this leaves after 10 minutes, which means this guy will leave at 10 minutes and after 20 minutes, and we're talking about the green. The green line, it leaves after every 10 minutes, which means after every 10 minutes or 20 minutes. Sorry. Okay, so after every 10 minutes, 20 minutes, 30 minutes, 40 minutes, and so on, this guy leaves. Okay. And then purple bus leaves the bus after every 20 minutes, which means that it leaves after 20 minutes and leaves after 40 minutes, 60 minutes, and 1 hour, 80 minutes, and so on. And I mean, you can always, the thing is that we are doing it this way is I want you to figure out whether you have to do this by whether you have to find out the LCM or HCF, because it's not given in the question whether you're supposed to find out the LCM or HCF. Okay, so purple, green, I think this is red, sorry. This is about the red bus. Red, and the purple bus leaves every 35 minutes, which means it would leave first at 35 minutes and then at 70 minutes and so on. Okay. Now I want to know the time after how many minutes will all the 3 lines leave the city at the same time, which means I need to find out the time which is common across all of them. Okay. What do I need to do? These are all multiples, and I need to find out the smallest time after which they leave the terminal at the same time. So I think you can already tell that I'm looking for an LCM. And so what I can do is I can put all of them together in a single table, because over here, instead of doing the separate single table, separate table prime factorization, I could just do a single table factorization because I'm not given the factors, right? So I could just do the single table factorization. So first thing to realize, I think the first objective of this question is to realize that this is an LCM question. Okay. I'll draw a single table. So 10, 20, and 35. And if you remember, while we're doing LCM, we pick up the smallest prime number that divides any of these numbers. So I'll pick, for example, I'll pick 2. So 2 5s are 10, 2 10s are 20, and then 35 will remain as such because, well, it's not a prime number. It's not an even number. And then you pick 2 again because 2 doesn't divide 5, but 2 does divide 10. 2 5s 10, and then 35 would remain as such. I think the next thing I would do is pick up 5, right? So 5, 1, 1, and 5, 7, 35, and then I will pick 7, 7, 1, 1, and 1. We're going to solve all the way to the end. Okay, that's what we do in LCM. And then LCM would be 2 times 2 times 5 times 7. 2 times 2 is 4, 4 times 5 is 20, 20 times 7 is 140. So after 140 minutes, the buses leave the terminal at the same time. After how many minutes? After 140 minutes. Okay. This is, I need to figure out that this is an LCM question. Okay. Next question is similar, but the only difference is, if you read the question, although you're supposed to do this by yourself, I'll just give you the hint. What's different in this question? The following bus route A leaves the city in the next 5 minutes. So the same thing, the only difference is now we have A, B, and C instead of red, blue, and purple. What was it? Red, purple, and I don't know. So 5 minutes, this is 6 minutes, and after every 9 minutes. Now, if you notice, here is the difference in the question. When is the next time? Okay. Previously, the question asked in how many minutes? So we were supposed to give the minutes, and our answer was 140 minutes. Our answer was 140 minutes. Now, in this question, you're not supposed to give the minutes. You're supposed to tell after what time after 13 do the buses all leave together. Okay, so let's say you take out the LCM of 5, 6, and 9, and let's say it turns out to be 90 minutes. Okay, I'm just taking a guess. Let's say 90 minutes. So you should be able to tell what time is after 90 minutes of 13. 90 minutes, I think, is 60 plus 30. 60 minutes plus 30. 60 minutes is 1 hour and 30 minutes. So it's actually, if you do 13 plus 1 hour 30 minutes, so I think it will be 1430. 1430. Yeah. The next time the buses would leave together would be 1430. Okay. Maybe your answer could be different, whatever the answer you get over here. Convert this into hours and minutes, and then find out the time, not the time in minutes. Okay. Previously, we just told the minutes. 140 minutes after 9 p.m. or 9 a.m. or whatever. Okay, but over here, you have to tell the time. So the answer would be 1430. Or something like that if the answer is, if your LCM turns out to be 90, which you have to figure out. Okay, I'll let you do this by yourself. The last topic, and the very important one, and that is rational and irrational numbers. Now, if you look at the name of the rational numbers, the name itself gives out the hint. Rational, half of the word means ratio. That means it's still that it's a ratio. So what are rational numbers? Rational numbers are, which can be written as the ratio of integers. I hope you remember when we were talking about integers, I told you that in the very first topic, I told you that we'll be using the concept of integers over here. Okay. So anything that can be written as a product of integers, as a ratio of integers, can be written. This is also important. It's not always written. For example, if you look at 1.5, it's not written as a ratio of integers, but I can write it. 1.5, I think, is 15 divided by 10. Yeah. Okay. So integer on top, integer on bottom, it is a rational number. A ratio of integers, how can you write something as a ratio of integers? P divided by Q, where P and Q belongs to integers. This thing means belongs to. Z means integers. It could be positive integers. Z means set of integers. Actually, I'll write it. Are integers. And Q is not equal to 0. The denominator cannot be equal to 0. Okay, that's the condition. In any fraction, really, not just rational fractions. In any fraction, you cannot make the denominator 0. Cannot be 0. Okay. Now, I said that, let's take a few examples, I think, of rational number. For example, 9 over 2 is a rational number. -5 is a rational number. How? It's not written as a fraction. I could write this -5 over. So it will be integer on top, integer on bottom. Perfect rational number. Okay, if I write 0.5, for example, it looks like it's a decimal and not a fraction, but I can write 0.5 as 1 over 2, which is a rational number. Okay, now, which means sometimes some rational numbers are written as decimals. They're hiding behind decimals. So you have to spot out, you have to be able to tell which decimals are rational numbers and which decimals represent, which decimals do not represent rational numbers. Okay. So what could be the way to do this? Well, how to spot a rational number when it is just written as a decimal. Okay. I mean, in a fraction, you can already tell, but when it's written as a decimal, that's when it is a problem. Okay. So here's a tip. Decimals that, there's one sentence that you need to learn, and that is decimals that end or repeat. As simple as that. Decimals that either end or repeat themselves, those decimals represent rational numbers. Decimals that end, those are called terminating decimals. Okay? For example, I just gave you an example of 0.5. It's a terminating. It ends after 0. It ends after 5. You can write it as 1 over 2. Okay? For example, it's 0.75. You can write it as 3 over 4. Okay? If it's 0.25, you can write as 1 over 4. So these are, because they're terminating decimals, right? They terminate at some point. They don't just keep on going on forever. And decimals that end or repeat. Decimals that repeat are called recurring decimals. Okay. What do we mean by recurring decimals? Well, recurring decimals are that, for example, 1.3, 1.3333, and the list just goes on and on. 0.3 actually, 0.333. If the list just goes on and on, it's actually equal to 1 over 3. Okay, we write it this way, 0.3, and we put a bar on top of it, which means that it's just going on and on. In short, all the terminating decimals and the recurring decimals are rational. Even though they don't look like that they're rational, but they actually are rational numbers. Okay. Well, what about irrational numbers? Numbers that are not rational are irrational numbers. It's as simple as that. Numbers that are not rational are irrational. It's like saying anybody who is not regular is an irregular person. If I were to ask you to define an irregular person and you give me a definition, well, anything that is not regular is irregular, right? In the same way, any number that is not rational is irrational. Okay. But again, we will not, of course, we're not going to settle for this definition. We will look at some, of course, they're hiding behind as decimals. So how to spot an irrational number when it is hiding as a decimal? Some irrational numbers are pretty obvious. Okay. For example, pi is the very, very, very common example. The value of pi is 3.141, and this goes on and on, never ending. Even the massive supercomputers struggle to calculate this. It's the value of pi. Okay, so it's super hard. Now, how do we do that? How do we calculate? Sorry. And the next way to spot irrational numbers is nasty decimals. So what are nasty decimals? Decimals that do not end and do not repeat. Decimals that neither do they end nor do they repeat. So definitely nasty. For example, if you get a decimal like this, 1.7139258311098657. It just goes on and on. Okay? And there's no pattern. They do not fit into any pattern. Those are called, they never end and they never settle into a pattern. If you notice, there's no pattern here. So definitely very nasty decimals. Those nasty decimals are called, they represent irrational numbers. Okay, pi is also one of the nasty decimals. It has infinite number of decimal values that, again, not everybody can calculate. Okay, the third way to spot an irrational number is a surd. Now, what's a surd? Any number that is not a perfect square hiding inside a square root. Any number, a number that is not a perfect square but hiding inside a square root. For example, if you take the numbers all the way from 1 to 10, think about it. If I were to square root every number, now, do you think it's a perfect square? No, sorry, 1 is a perfect square. So it is rational. It's not an irrational number. Is 2 a perfect square? No. So it is an irrational number. Irrational number. Irrational. 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 Is 9 a perfect square? Yes. 3 squared is equal to 9. The same over here. 1 squared is equal to 1. So yes, it is not an irrational number. It's actually a rational number. Square root of 9 is, I mean, we'll do square rooting later down the road, but I hope you understand. If you just put this in the calculator, you'll get a 3. So you will know that it is a irrational number. Square root 10 is also irrational. So only this is rational. And okay, square root 4, I think, is also a perfect square. So this is also rational. The rest are all irrational. Square root 1, 2, 3, 4. Square root 1, 2, 3, square root 5, 6, 7, 8. They're all irrational. Wait a sec. This is also rational. What am I doing here? Sorry, guys, I'm losing my mind. I'm getting tired now. Rational. This is also rational. Okay. Okay, next. Write down an irrational number between 3 and 4. Now think about this. How can I find an irrational number between 3 and 4? Let's say on the number line, this is 3 and this is 4. How can I find an irrational number between this? Okay, we know that irrational number has to be very obvious, which is pi. Pi is an obvious one. It's an irrational number. Nasty decimal. Now, what do I know which is a nasty decimal between 3 and 4? So the other way to do this is surds. Okay, we know that a perfect square inside a square root is a rational. Okay, and so between square root 4 and square root 9, everything is irrational. They're all irrational. Okay, so there should be a way to do this irrational. Define irrational number between 3 and 4. Can you write 3 as square root 9? Can you also write 4 as square root of 16? It's the same thing, right? So now I have a lot of irrational numbers between square root 9 and square root 16. And those numbers could be, well, square root 10, square root 11, square root 14. We cannot take square root of 16 because that would be then that would be a rational number. Pick up anything, for example, square root 10, square root 7. Okay, so if I'm required to just write one, no, actually you cannot take 7 because it has to be greater than 1 and less. It has to be between 9 and 16. I think square root 11. Maybe square root 12, square root 15. All of them are irrational numbers. So I'll say square root. I cannot take square root 7. I think I'll take square root 11. And I'm definitely losing my mind because I just wrote square root 7. And the number is supposed to be greater than 9. Right. Yeah, this is the last question and we'll be done. So guys, stick around. We only have last question to do. Circle the irrational number. So this is definitely irrational because 22 by 7, we have the numerator is an integer, denominator is also an integer, so definitely a rational number. So this is irrational. This is also irrational. Pi is a very obvious one. Look at this. This looks like that it is irrational because square root 2 is as a surd. Square root 2 is a surd. They're both surds. Right? But if you notice, they're being multiplied. So let's see if I multiply them. Multiply them in a single square root, it will be 2 multiplied by 8, which is 16. Square root of 16 is 4. Just 4. So do you think now it is a irrational number? Of course not. It is a rational. Okay. So if it were a surd alone, it would have been irrational. For example, if it were a square root 8 alone or square root 2 alone, it would have been irrational number. But now they're under an operation. Once I applied the operation, I realized that, okay, the answer is 4, which means it is a rational number. So I will not circle it. My irrational numbers are square root 3, 3 square root 2, and 7.